So let's talk on a rectangular rotating coil. I think this is the last topic which is there for the test. So we have a north pole like this. Okay, and a south pole here. So the magnetic field lines due to this thing will go from north to south. These are the magnetic field lines. Okay, and suppose I have a current carrying coil. Let it be a rectangular coil. Like this. Okay, so current is entering like this. So here will go like this. Here come like this. So here will go like this and come out like this. Okay, so this current carrying conductor or a rectangular coil will experience a, first you can say it's a force, and force at a distance will produce a torque. Okay, so the force on a current carrying conductor is given as TF equal to ideal cross B. This comes from force on a moving charge. This QV cross B. This force is called Lorentz force. And this thing comes from experiments. Okay, so using this thing, I can get this one because current carrying conductor is nothing but a collection of charges moving in one particular direction. So each charge will experience a force, and all the charges have the same V direction and B direction. So direction of force on A, all the charges will be same. So that they will add up to give the total force as ideal cross B. Okay, and if I take a small element here, the force direction here in this case will be DL is inside, so B is, so ideal cross B will be upward force. The force on this part of the conductor will be upward force. Will be dot direction. Sorry, current is cross, so force is upwards. So I should say the current is, the force is upwards. In this part of the conductor, force is vertically upwards. Okay, so we assume this as x-axis, this is y-axis, and there is z-axis. Okay, so the field is going in the I cap direction, and this rectangular coil, the plane of the coil is a XZ plane. This plane of this rectangular coil is in XZ plane. Okay, so the current is moving in the direction of minus K cap. Current I's direction is minus K cap. Okay, B is along I cap. Okay, so ideal field direction is same as I direction, so it's minus K cap. So minus K cap cross B direction is I cap. So A cross I is J. Okay, so minus sign will come because K I is 3, 1, that is 2, so minus J. So which is I is inverse, right? So I is minus K cap. Okay, B is towards, right? So I cross B, ideal cross B. The ideal cross B, that is downwards, so downward force. So this force here is downwards. So force on this left part of the conductor will be downwards. Okay, so if we take another element here, same thing applies. The force on this element will also be downwards. So all this force will add. The net force on this left part will be downward. This right
அட பாவி ஹரிஹரன், என்னடா பண்ணி வச்சிருக்க? ஸ்கிரீன்ஷாட் எடுத்து சும்மா மேல இப்படி ஒண்ணு வச்சு விட்டா.
So this part of the conductor will have all the forces in upward direction. So this coil will rotate in anti-clockwise direction, the direction of rotation. If you take this part of the conductor, I direction is towards right. Okay, B is also the same direction, so the force here will be zero in this particular position. Okay, but once the coil starts rotating, then it look like this from the side view. These are the two currents. Okay, the current is flowing towards right, right? The current is flowing like this. Okay, so now B direction is towards right. B I cap, and current is in this XY, or I should say one XY plane. Okay, so ideal cross B. So here the force will be ideal cross which will be into the plane of this one. Cross. So similarly, so this actually comes, this part of the conductor is this one, is actually this one, this part. Similarly, I can take this front part, this part of the conductor. So it will be something like this, and the current will be in this direction. Okay, so this is in the current direction as reverse, so this is being forced in this top direction. So this conductor is here, this part. So here, this part of the conductor is experience a force in this cross direction. So if this force is this way, on this conductor, it is this way the force. Okay. This force is like this. Okay. This force is opposite. So these two forces will cancel. Okay. This force is on this side is a downward force. And here is an upward force. So this will produce an anti-clockwise torque. Okay. And so this torque, finally, if you write this torque as force into distance, into the perpendicular distance. Okay, this force and this is this distance is say 2a. Okay, so that will be force into a by 2. The breadth of the coil is a. See, a by 2 into, sorry, force into r perpendicular is a by 2, and then some angle will come. This force from this middle axis. Okay, so this length is a by 2. And this separation is theta. Okay, this angle is theta. So this perpendicular distance come out to be a by 2 sine theta. This distance. And then two of them. So this torque will be this left coil, and there is a torque will be this right conductor. Okay, so this will come out to be Fe, and this force is ILB. For an element, it is IDLB. For the entire length, it is ILB. Okay, you write that. ILB, and then A by 2 D is A, and then sine theta. So this L into A is the area of the coil. And then this into I is I into A into B. into sine theta, and this I into A is the moment of the coil. So this formula will come out to be M cross B. Okay. Another thing is this torque will be maximum if the coil is in this position, because in this position, the force is at a maximum distance from this axis. But if this rotated by 90 degrees, so then the coil will look like this. In that case, the force will pass through the axis, so the torque will be zero. So this will have a torque of zero. In this position, the torque will be maximum. So here the angle between the area vector, which is the normal to the area. Area vector is defined as a normal to the area, and this field, magnetic field, is 90 degrees. So torque is maximum and angle is 90 degrees. Angle between the area vector, that's area of the coil, that vector, and the magnetic field direction is 90 degrees. Here in this position, the area vector is normal to the area, so it's towards right. Okay, and B is for same direction. Okay, so here torque is zero, and sine the angle between the area vector and the P vector is 0 degrees, so sine 0. So it's basically consistent with this relation or this formula. Torque is M cross B, and you can remember like torque is maximum, the power is in this position because the force is at a maximum distance from the axis. Because torque is R cross F, so to increase the torque, when the force is fixed, I have to increase R. Okay, here the force is fixed, even the coil in a rotated position, this ILD will not change because even the coil is in this position, the angle between I, which is into the paper, and B, which is towards right, is 90 degrees. There is no change. So force is same. The only way the torque can change is the projected distance from the axis. So here the projected distance is moved in this position, and the coil is rotated 90 degrees. The distance is 0, so the torque is 0. I think this thing is there in your book.
Yes, sir.
Just a minute. Yeah, page number 658 of the theory book, integrated textbook, page number 58. So it's basically conveying the same thing. Okay, and one more thing is, see, if I leave this, okay, this coil will rotate, but if I connect a spring to this coil, so once I have this coil in this magnetic field, and there's a magnetic field here, so there'll be a torque which will try to rotate this coil. So if the coil is free to rotate, keep on rotating, but if I attach a spring to this coil, something like this, okay, like a spiral spring. Okay, so once this thing coil starts rotating, the spring will get wound, and depending on the torque value, this thing, the amount of what should I say? The amount of coil, the angle by which the coil is rotated will change. It's like a linear spring. So here this is a linear spring. Okay, if I apply a force, you'll get compressed by a certain amount, say x. The amount of compression will stop when this kx equal to f. Okay. So if this increase means the x will, the amount of compression increase. Similarly for a spiral spring, okay, when I try to, this is a spiral spring, when I try to apply a torque, okay, it will get rotated by a certain amount, say amount theta, okay. And the torque, when the applied torque is equal to k into theta, theta will not change. So if I know the theta value, I can know the torque value. Okay, similarly, in the spring balance case, we have a linear spring, okay, and we attach a mass to it. So to know this mass value, I can find this x. X I can measure from the scale. From this, I know kx equal to m into g, and g value is known. So from this I can, K is a spring constant, which will be given, depends on the spring. Once K is known and the extension is measured, I can find the value of M. Similarly here, the torque I can measure knowing the constant of this spiral spring constant, and also the value of deflection or the amount it has been rotated. So this is known, I can find torque. Instead of having a spring, I can also have a thread sort of a thing. Like this is like a thread which is fixed to this one end, and other end this rotating coil is there. Okay. Just a minute. Other end is coiling there. So when the current is flowing through this one, present the magnetic field, it will develop a torque. But once this thing rotates, this wire will start rotating, right? But this wire will resist. This is like a spring. So this will rotate by a certain amount of theta. After it will stop. And this theta is equal to supply torque tau as tau equal to K into theta, where K is the constant of this wire. Okay, this is like a spiral spring. When you try to rotate, it will resist, and the amount of rotation depends on the amount of applied torque. So knowing this value of theta, I can get the value of torque. And if this torque, obviously the torque will depend on current. Okay, so once I know this theta value, I can get the information about the current value. This is basically ammeter. Ammeter basically, I pass the current through this coil. I measure this theta from the reading of the ammeter scale. From that, and I know the constant of this ammeter is K. So once I know K, I can find the value of current. This is how ammeter works. But this is not in this syllabus. We stop up to the development of the torque of a rectangular coil. Okay, so exercise 3, last question, question number 28, page number 67. Just open your exercise book. Question number, sorry, page 67, question number 28. Page 67, question number 48. So if I've done it, it's fine, but otherwise just we'll do it now. So there is an infinite wire carrying a current I. The current flowing is I. Long straight wire. And there's a rectangular coil here. And current is flowing in this coil. Okay, so once the current is flowing here, there will be a interaction between two currents. That way I can think as interaction between one current and the magnetic field produced to be the other one. So if I call this one, this straight current will produce a magnetic field at this point. If I call this B1, okay, and that will interact with this current, and we call it I2. Okay, so the force on this left part of this conductor or the coil, that will be I2 PL cross P1. This current will be called I2. Second one. So this force I can find out, and B1 here, B1 that you can get from Ampere's second law. B1 is mu naught I by 2 pi R or T, but T is the distance right now. For this is the distance. Let me call it T. Okay. And okay, whatever. Let it be given and just okay. So this P, and similarly this part of the coil, which is the right conductor, is a resistance say D2 from here. And the current, sorry, magnetic field due to 1 will be a different value. Let me call it right. And let me call this thing left, the left conductor. Okay, so V1 at this right conductor, okay, will be less than V1 at this left conductor because D2 is more than D1. Magnetic field goes as 1 by D. Okay, so and what is the direction of the force? Direction of the force is ideal cross B. So here ideal is upwards and B is downwards. So what is the direction of B? Okay, ideal, if I take it as direction as ideal is J cap and B is minus K cap. Because this is X, this is Y, and this is Z. Okay, so I2 is J cap upwards, right? And then B due to I1 is into the plane of paper, which is minus K cap. So J cross K is I, and minus sign is there, so it's minus I cap. So it is towards left. Obviously, there's an attractive force, no? Between two parallel currents will be attractive force. So the force on this one will be towards right. Anti-parallel currents will be a repulsive force. What is the magnitude of the force? Since the magnetic field in the right is weak, this force magnitude will be smaller. I'll make it a shorter arrow. Force on this right conductor will be shorter. Okay, so they'll leave a net force towards left, and force on this the top part. For that ideal, current direction is I cap, and B direction is minus K cap. So I cross K is minus J, will be plus J cap. Okay, this one will be, so it will be upward force, and this one will be a downward force. And these two forces will be equal. Because the force here and the force here, one is upwards and one is downwards, and both are equal magnitude because both these elements are the same distance from this straight wire. So they have the same magnitude and they have the same current. So these two forces are equal and they'll cancel. And the force at this point will be more compared to, slightly more compared to this one, but exactly opposite part here. The force will be slightly more, but in the opposite direction. So the force on this top conductor and the bottom conductor will cancel. So the net force is towards left. Okay. So move towards the wire. So option C is true. So once option C is true, should be false. And rotate about axis parallel to the. Obviously, it will rotate, but here the direction of force is. Now it will not rotate. But slightly move from this disturbance position, then will start rotating. What is the option? Only is 3 only. Will not rotate because the torque here is 0. Okay, torque. Suppose it has to rotate means it has to rotate about some axis of this, right? Okay, so this force is perpendicular to this axis, so not rotate. If the force is at an angle to the axis, one component will be along the axis and one will be okay. Let me consider this example for door. Say this is a door and this is the axis. What I want to say is only the force which is in the tangential direction. So that is it. This is the tangential direction. Ft. Only this force will produce a torque and make this door rotate. The other force, which is say along the z-axis, say the vertical axis is z-axis. So Fz, and also the force which is along the radial direction. This will not produce any torque. Only this tangential force will give me torque. You can just figure this out. You have a door. If you have to make it open or close, you have to apply a force in tangential direction. Only that force will try to rotate it. The radial force just try to stretch the door, so not rotate it. And this vertical force Fz will try to bend the door. You not try to rotate it. Okay. So if force is applied in some arbitrary direction, say like this, then I do first split this force into three components. One is plane of the door and perpendicular to the door. Perpendicular to the door is the one which will be tangential. Okay. So one I can resolve in the plane of the door and one is perpendicular to the door. In the plane of the door will be the radial force. Okay. Even for this along the door, I can split it two components. One is radial component, other is this vertical component. Okay, so this is the basic idea. Force I can split into three components. One is the radial component, one is the tangential component, one is the vertical component. Okay, and this radial component, tangential component will form a circle, and this door is moving in that plane of the circle. Okay, so here this force is actually a radial force along the radius. Okay, this force and this force, so it will not put any rotation. So is this clear? Any doubts?
Yes, sir.
The theory part is okay, done after some time back. So okay, well, one more thing. For motion of charge particle in electric and magnetic field, general situation, there will be some electric field, okay, and there will be some magnetic field. So the charge is there and it's moving some velocity v. So the force of this charge due to electric field will be QD. Okay, and then due to magnetic field will be Q into P cross P. Okay, so this thing is the general force relation. But if we take some special cases, for example, say E is towards right, okay, and initial velocity also towards right, and B is also towards right. The case one. Okay. So here in this case, the force will be some Q value in the electric field is there along I cap. Okay, and then B is along I cap, the initial velocity, and B is along I cap. So this will be zero force in this particular case. So here the charge particle will move only due to the electrical field and it will move along the x-axis. So it will continue to move. Initial velocity, this one will continue to move in this straight line. Now, one more thing. Once it starts moving, the velocity component is there, but still the velocity direction is I cap, which is same as the direction of the magnetic field. So this force will still remain as zero. Okay, I can complicate this thing a little bit. I'll say V is around, say case 2. V is around, E is around, say, x-axis, and V is also around x-axis, but V is, say, into the plane of paper. And let it be uniform. Let it be not complicated. Let it be a uniform magnetic field. E is also uniform. Okay, let me take simple cases. Now the force due to this electric magnet will be whatever the charge Q into E plus QB cross B. Okay, so since now the direction of magnetic force will be perpendicular to both B and B, the direction of the force will be, suppose the charge is here. Charge is here of value Q. Okay, QV cross B, the direction is B is into the plane of paper, right? So B cross B will be upwards. And since we have this thing, velocity is, sorry, the magnetic force is perpendicular to the velocity, we'll try to bend this velocity vector. So try to make it a circular motion, but this force will take this thing towards right. So the motion will be something like this. Actually, still simpler case than this will be, okay. Okay, so this thing, even if we don't have initial velocity, if we just have this charged particle and the electric field is towards right, and the magnetic field is say cross, to start with, the force will be an initial velocity is 0. So u is 0. Force is QE plus QV cross B. To start with, this force will be 0 because V is 0. But once it starts moving the direction of the electric field, V is there. So this force will start acting. Okay. So then it will be a circular motion and also it will move towards right. So it will be like this only. So I don't need this initial velocity because electric field is there. So you need this without this initial velocity. Once this electric field moves this thing towards right, so that will give a force to the magnetic field. So this way you can solve any problem. You open a theory book, they are considered a lot of cases for this motion. This one.
Sir,
What?
sir, can you solve 21st question, sir? Exercise 3.
Exercise 3,
21, sir.
page number
65.
question 23. A metallic wire is folded to form a square loop. It carries a current I perpendicular to the shape. Okay. I tried yesterday, no. Okay, I'll do it later. Leave the question for time being. Any other question? Motion of charge, they consider different cases, no? Very good. Case 1. Yeah, they consider 4 cases. So in any case, see whatever the electric field magnetic field given and the charge, some charge. Okay, so I can write this force equation Q E plus QV cross B. Okay, and this force is nothing but mass into acceleration. Okay, in acceleration I can write as m into dv by dt. Okay, so if the right thing is known as a function of time, I can get velocity as a function of time. So I can solve for V by solving this equation, and I could also write this thing as m into d square r by dt square. So this also give me the r as function of time, which is basically the path of the particle. Okay, so in principle, if you given electric field and magnetic field and the charge value q, I can find its velocity, how will it change in time, and also how the thing will move, the path. So in principle, it's solvable, but it's easy to solve in particular special cases. Okay, so I think there are some questions based on this one where you can find the velocity given the electric and magnetic field. Question number 5, page number 69. A charged particle Q of mass moving from origin under the action of electric field. This we can do after the break. I just mentioned the question number, page 69 of exercise book. 69, question number 5. Okay, we'll solve after the break. Okay, we just try if we have time.